Hello, today we are continuing the central limit theorem, and we are going to first start with talking about just the mean and standard deviation of a sampling distribution. So if we go back, the central limit theorem is the fundamental theorem of statistics. If we're looking at a few different, this is what you should have gotten from your simulation the other day. If you are looking at a set of population distributions, it doesn't matter if it's uniform, flat across, like rolling a die, symmetric if you're looking at the average height of American women, or something that's skewed right, say the salaries of MLB players. It doesn't matter what the original distribution looks like. If you take continued samples of size 100 and take their average, so if you take a sample of size 100 and then you take another sample of size 100, another sample, another sample, another sample, and you continue to sample it and take their average, the central limit theorem tells us that the averages or the sampling distribution will become nearly normal. So our sampling distribution is when we plot all of our X bars. Now the mean and the standard deviation look a little bit different. The mean is still the mean, so the center does not change. However, the standard deviation is sigma over root n. So we have a little bit of a different scenario when we're looking at the z-scores. So we're going to look at some examples today, and the first one is just going through and just calculating the mean and standard deviation. So this was in your notes. Go ahead and read it, highlight the important information, and then we will go over it. Okay, so hopefully you had a chance to do that. If not, you can always go back and pause. So here we are looking at the heart rates of 20-year-old athletes. We know the mean is 135 beats per minute. The standard deviation is 18. And we're looking at the sampling distribution of the sample means. So when you see sample distribution of sampling means, that's what tells us we're going to use the sigma over root n to calculate the standard deviation. So the first one, we have a mean of 135. The center stays the same. And then your standard deviation is going to be sigma over root n. So our original standard deviation is 18. We're going to divide that by root 10 because it's our sample size, and we get 5.7. Similarly, in the next one, we have n equals 25, so our mean is still 135, but now that denominator becomes 25, and so our standard deviation, if you take samples of size 25 instead of size 10, goes down and becomes 33.6. Go ahead and try out the other two on your own. If you go through and you do the other two on your own, you should see that you get a standard deviation of 1.8 and 1.04. Notice that as that sample size goes up, the standard deviation goes down, which makes sense because as the denominator goes down, then the denominator goes up, then the standard deviation goes down. Denominator increases, then the quotient decreases. So now we're going to go ahead and look at the difference between what we were doing before, just a regular z-score, versus what we are doing now. So this is looking at a braking distance of a Toyota Camry. It does tell us that it's normally distributed. We have a mean of 149 and a standard deviation of 5.28 feet. If we're looking at a single Toyota Camry, that tells us that our sample size is 1. So n equals 1 in this case. We're looking at one single Toyota Camry and comparing it to the rest. So we're not really taking a sample, we're just looking at a single one. And we don't say anything about the means here because you can't take a mean of just one item. So we go through and we can use our regular z-score. I would recommend always first drawing your picture. So over here on the right, you see that we have the mean in the middle of 149, and we want to know the probability that we are less than that. So that's why we shaded this region to the right over here. Then we go through and we find the z-score, x minus mu over sigma, and we get negative 1.7. I would recommend pausing and making sure you get that same number. The last thing that we do is we figure out the probability that occurs. I would not stress out about the notation here, but we're really looking at the probability of having a z-score, or the area under the curve where your z-score is less than 1.07. You're going to norm CDF that, just as we've been doing all along. Your lower bound is going to be negative 10. Your upper bound is that z-score of negative 1.7, and that's where the 1.04 comes from. We switch gears in the next example, and basically here we're looking at the 20 Toyota Camrys. Notice here we're looking at 20, so we do have a sample size. So here n is 20, so things get a little bit different. And then the key word is what's probably the average braking distance. So as soon as you see that word average and you have the sample size pop in, that's when you know that you're going to go through and use a z-score. So we're going to use very similar steps here. We're drawing basically the same exact picture, but now you're looking at an X-bar distribution. So this is it's a small detail, but it's really important that in part A we were looking at X, and here we're looking at a whole bunch of different samples of size 20. So when we find our z-score, notice that now we're dividing by root n, and we still have our x minus mu on the top, so it's the same numerator, and then the denominator is 5.28, now divided by that root 20 to get our 7.62. Now when you see this, you should really think, wow, because we know that 99.7% of our data fall within 3 standard deviations of the mean. So if this is over 7 standard deviations from the mean, we know that that is very, very unlikely. We don't even have to plug it into a calculator. We know it's so unlikely that we're going to get 0 or something really, really close to that. But just for kicks, you can go ahead and norm CDF that, and you'll get that probability of essentially 0. Having 20 Toyota Camrys that stop in less than 140 feet on average is so unlikely if the true mean is indeed 149. Now, a friend of yours tells us, well, actually, we can't do that because we're really in central limit theorem. The rule is you need to have a large sample size of 30 or larger. And too bad you actually had one of 20 cars. That's too low. You can't do the math. You can't use Z because of that. Well, he is wrong, because if you go back to the original distribution, it does say that it's normal. So as soon as something's normal, its sampling distribution will also be normal. So it's okay that we have the smaller sample size here. I would recommend trying the next one on your own, and then I will walk through it as well, but see how far you can get, and you can always pause me and go back and re-listen and try it as many times as you want. So the next one is very, very similar. We are looking at what's the probability that the average time spent, 25 minutes is our average time spent driving in the car with a standard deviation of 1.5, and we have a sample of 50, and we're looking at the mean time that they spend is greater than 25.5. So those key things here are looking at the mean, and that we have a sample size, which is saying, hey, you have to use the central limit theorem. So we're going to do the same thing we did in the last one. We're going to go ahead and draw our picture. So our mean is at that 25 is what it says the average is in times in the car. And we're looking at the probability that we're over that amount of over 25.5. So we're on the upper end of the curve. So after you draw your picture, go ahead and find your z-score, x minus mu over sigma over root n, and you get 2.36. Now you also know that this is unlikely because this is over 2 standard deviations away from the curve. As soon as you get this number, you are not done. Now you're going to go ahead and norm CDF it. Once again, I would not stress out about the notation, but this is reminding you that you're looking for the area under the curve. This is the area that you are looking for as you go through and do it. So in order to find the area, you have to norm CDF it, and your final answer is that 0.009. Now in this one, why is it important that we have to be over 30? Well, we don't know. It says nothing about the distribution at the beginning. It just tells you that you have some certain distribution. So the fact that it's 50, we don't know the shape of the original distribution because our sample size is large. We know due to the central limit theorem that the sampling distribution of x bar will be approximately normal. Go ahead and flip it to the back page, and we have one more example. And this one is looking at time people spend going through airport security. Once again, highlight the important information, mean, standard deviation for the amount of time they have. It does tell us it's normally distributed, so that's nice because we don't have to check our sample size. And we want to know the probability that they have to wait more than 25 minutes. All right, so draw your picture. Here's your mean at 22. And you're looking at over 25, so you're looking at this area on the upper end of the curve. A person is looking at one single person. So notice here I did do over the root n, just let's say you want to use that one all the time. That actually ends up being okay because root 1 is just 1, so it doesn't actually change your z-score. So you don't have to use this one. In fact, I wouldn't recommend it, but if you're worried about it, you know that the root one will end up being okay. So either way, you'll end up with 0.714 for your z-score. And then now we take that and we norm CDF it in order to find the area under the curve. So that 0.238, that is your final answer as you go through and do this. So you norm CDF it, our lower bound of 0.7, our upper bound of 10, and then we get that area underneath the curve. The next one, now we're looking at the 8 people. So 8 people in this case, we now have that sample size pop in. That's a super tiny sample size, but that's okay because we already know that it's normally distributed as it states in the problem. And we want to know that the average wait time is less than 25 minutes. So once again, a really, really similar problem, but now we have a sample size. And as soon as you see that average, now you're looking at the sampling distribution. So draw your picture. You have a very, very similar picture pop up. So you're looking at this upper end of the curve. Go through, find your z-score. Notice that when your numbers stay the same and all of a sudden you're sampling, we see that standard deviation on the bottom go up. And so as that goes, the number n goes up, so the standard deviation goes down. So your z-score goes up. And so your total area at the end of your 0.0217 also will go down when you norm CDF it, which makes sense. 2 standard deviations from the curve, we know that we're going to have a low probability.